Hi, yeah, in this video, I will show you how to fit a simple logistic regression model using R. Okay, so first let's read in the dataset. And you can see this dataset has two variables, fate. So that will be our dependent variable. It's 0 and 1. So that's the dependent variable for logistic regression model. And then Apache score, we consider it as continuous. So here, to fit a logistic regression model by using the R function GLM, GLM stands for Generalized Linear Models. The syntax is quite simple. So here, GLM fate regressed on Apache, data equal to data, and family equal to binomial. So when you specify family equal to binomial, then it automatically select logit as the link function. So we're fitting a logistic regression model. And of course, you can fit any distribution in the exponential distribution family. So if you say family equal to Poisson, and the dependent variable is a count, then you will be fitting a Poisson regression model. So let's fit the model and print out the summary. You can see this pretty typical outputs from the GL model fit for logistic regression. You can see the null deviance, residual deviance. We're going to use those to compute some goodness of fit statistics, like the pseudo R square later on. And you can see the AIC value down there. As you know, in generalized linear model, the parameter estimation is done by maximum likelihood estimation, which is implemented by iterative reweighted least squares. Okay, so that's why we have the AIC value, which will be very useful for model selection. All right, and in the coefficient table, you can see the independent variables, then the estimate column, that's for the betas. And you got standard errors, you got Z value, and you got a P value. And the P value is for testing whether the true beta equals 0 or not. So here, for Apache, the P value is very small, so there is a significant effect of Apache on fit. And this is really basic output from logistic regression model fit. We can do a lot more. So first thing I want to show you is compute the confidence interval for regression coefficients. Okay. So now it's really preferred for us to present confidence intervals wherever possible. Okay. So to compute the confidence interval, it's very easy here. We use CONF-INT. Just compute that and then just print it out. So you can see the 95% confidence interval down there. And furthermore, the default is 95%, but if you say, oh, I want a 90% confidence interval, you can use the same function, CONF-INT, but then you can use the option, this argument level equal to 0.9. Okay. You can specify any significance level here. Okay. So let's try that. Print it out. Now you get another 90% confidence interval computed here. Okay. All right. And you have learned that an advantage of logistic regression is that you can directly get an odds ratio estimate by just exponentiating the beta, right? So we can do, we can calculate odds ratios here. So first, let's just extract the coefficient by using the command COEF coefficient. Then we can just say the odds ratio equal to exponential of coefficient. And then we can compute the confidence intervals by computing the standard error for the coefficient. So in this command, summary of model at coefficient, and then we say we want standard dot error. Okay. So store that in SE, and then we can use these formulas to calculate the upper limit, lower limit of the confidence intervals for odds ratios. So lower and upper. And then we can put everything into a data frame. And then let's print out the data frame. So you can see this is the odds ratio, and this is and then the lower and the upper limit of the 95% confidence interval. Okay. All right. Next is really we want to test if an effect in the logistic regression model is significant or not. And remember, there are 3 tests. One is the likelihood ratio test, and the other is the Wald test, and the other one is score test. Okay. So here, let me show you how to do the likelihood ratio test first. And remember, the likelihood ratio test is nested. It has a nested model. So first, you need to fit a smaller model. Now we call it the model 1. So this is a model with only the interceptor. So let's do that. So it's really implemented by just GLM fit regress on 1. And then we fit a more complex model. So we call it model 2. This is actually the model we fitted. The fit regress on Apache as a logistic regression model. We call it model 2. And then we can just use the R function called the LRT. Not RLT, sorry. The function ANOVA. So model 1, the smaller model, then model 2, the larger model, and we specify test equal to chi-square. Okay, so we bring it out, and this gives us the test result, and also it's highly significant. Okay. The next one is the Wald test. So I found our package called AOD. So I installed it here. And so I'm not going to install again, so I just load it. And then let's fit the model again. And then you can use Wald dot test. And the B equal the coefficient, and the sigma equal the covariance matrix. Terms equal to C2 because we only want the Wald test on the Apache score. So here, and we can print out. So this is the Wald test using the Wald dot test function in the AOD package. The p-value is 0.0095. And if we print out again the original logistic regression output, you can see the p-value is 0.00952. So actually, by default, it is like a really close Wald test. Okay. And then for the score test, I was not able to find a package directly implemented. So I did a little bit of programming on my own. So we did coefficient, covariance matrix, then we can calculate the score test statistic using this formula. And then get the degree of freedom, then calculate the p-value, and then just print out the p-value. So the score test also indicate very significant effect of Apache score. Okay. All right. Another task is to calculate the predicted probabilities. We can just use the function predict and the type equal to response. In the future, we can use this for residual plots. And then we can calculate McFadden's pseudo R squared. So that's sort of like the R squared in multiple linear regression, but not quite. But we can calculate the null deviance, and then the residual deviance, and then the McFadden pseudo R squared is calculated in this 1 minus residual deviance over null deviance. Okay. And print it out. So it's about 42.7%. Okay. And then for goodness of fit, we can perform the Hosmer-Lemeshow goodness of fit test. And for that, we need the library called resource selection. And we can use the function HOSLEM, so Hosmer-Lemeshow dot test. And then this is the syntax to implement the test. And then you can print it out. So the p-value is 0.4269, so indicating our model is an acceptable model fit. All right, that's all for this video. I'm gonna make another video showing additional topics such as the goodness of fit and ROC curves, etc., etc. Okay, thanks.